Hey guys, one of the frustrating thing about learning A/B testing is how you calculate the sample size. You might often read literatures about, some sample size formula, but how is that formula actually derived? And that is something that you have to build intuition on if you want to succeed in product data science and also prepare for interviews. So hopefully in the next couple minutes, I can provide some information you need in order to understand how sample size is calculated. So let's just start with the definition of sample size calculation. What you're trying to do is you're trying to calculate sample size based on the underlying statistical model, significance level, statistical power, and minimum detectable effect. Now, when you look at literatures on sample size calculation, you often see this formula, which is n equals the z critical value of the significance level, sum of the z critical value of your statistical power, and then this sum is squared, and it is multiplied by the variance of the point estimation divided by the delta squared. So if I were to label what each of the parameter means, what you have is the following. So this n represents the sample size per group. It's not the sample size that is required for the entire experiment. When you're running an A/B test, you have a control and a treatment condition. So this calculation basically means that this is sample size that's required for one of those two groups. So you would have to multiply by 2 in order to get the sample sizes that are required for the entire experiment. Now this z critical value represents the one for the significance level. And that's something that we're going to talk about in a bit more. And we also have a z critical value of the statistical power. And then we also need to estimate what the variance is, which is not a straightforward process. So that's also something we're going to do more of a deep dive on. And this numerator is divided by the delta squared. And this, keep in mind that this delta squared, it is not the same thing as lift. And that's something that I will clarify more on. Now let's start by understanding the significance level. So when you look at the significance level, it is essentially a threshold for which a p-value of an observed effect is considered as statistically significant. But what does that really mean? Well, basically it means the following. If you observe an effect, right? You ran an experiment, an A/B test, and you see that there's an improvement of your KPI of interest. So let's just say sign-up rate. And it is better for the treatment than what you saw in the control. But the question is that the effect that you observed, the difference between the two, did it happen because of some random chance or because of the underlying difference between the treatment effect versus the control effect? So you need to evaluate the statistical significance of that effect. And the way you gauge that is comparing the p-value, the probability of observing the effect or more extreme, under the assumption that the null hypothesis is true. And if this p-value is less than the significance level, the alpha, your rejection region in this case, then you would deem that effect to be statistically significant. Now this null hypothesis has a following distribution, a null distribution, and you're trying to calculate the probability of observing the effect or more extreme under this null distribution, because remember, you're assuming that the null hypothesis is true. Now this null distribution, when you're evaluating using a statistical test, is normalized in standard normal distribution. And what standard normal distribution is you're essentially scaling your data in such a way that the mean becomes 0, and then the standard deviation becomes 1. Now, in most statistical tests, oftentimes, it is a two-tailed test. And what that means is that the effect may be in the negative direction, meaning the control might be worse than the treatment, or it might be in the positive direction, meaning that the treatment is better than the control. And because this is a two-tailed test, you have to split the alpha in this case. So you allocate half of it by dividing alpha by 2. So one of the region on the left side is going to have alpha divided by 2. And then the region on the right is going to be alpha divided by 2 as well. And the threshold applied on this scale that creates this rejection region is going to be the z critical value, or the z-score. So on the left side, this is defined by z-score of alpha divided by 2. And on the right side, this is defined by z-score of 1 minus alpha divided by 2. And you could think of the subscript as the percentile that is applied under this probability distribution. So let's presume that alpha is 0.05. Then what this means is that you're trying to find what is the z-score of the 2.5 percentile under this null distribution. Whereas on the right side, 1 minus alpha divided by 2 is going to give you 0.975. So you're trying to find what is the z-score that represents the 97.5 percentile of this distribution. Now, one thing I want to tell you is that when you are interviewing for a product data science role, questions involving how to calculate the sample size is a fair game. It might require you to recall what is the corresponding z-critical value for a given alpha. So I want to lay this out for you because I think it's really helpful. So common set of alphas that you often see in A/B testing or just statistical testing in general will be 0.01, 0.05, and 0.10. And oftentimes the statistical test is going to be two-tailed. So the corresponding z-critical value for the alphas in this case is going to be 2.58 for the alpha of 0.01, 1.96 for the alpha of 0.05, and 1.64 for the alpha of 0.10. Now notice that this z-score is the one on the right side because the subscript is 1 minus alpha divided by 2. What if you're trying to get the z-score for the left side? Whatever z-score value you have on the right side, you can apply that to the negative region as well. So let's proceed in the next concept that we need to cover, which is the statistical power. The statistical power is the probability of detecting an effect given that the effect exists. What is the underlying difference between the significance level and statistical power? So the underlying difference between those two is that the statistical significance gives you the statistical evidence you need in order to reject the null hypothesis or not, with the null hypothesis often claiming that the two distributions are the same. However, this doesn't give us a sense about what is a probability of detecting an effect if that were true. So how do we get the power in this case? So statistical power is the region covering the intersection of this critical value on the null distribution. So whatever is to the right of this critical value is going to be your statistical power in this case. So if you have this null distribution and you have your z critical value, you would calculate what is the z-score on the alternative distribution that intersects this z critical value that is on the null distribution. And the region to the left is going to be your beta, the type 2 error rate, which is the probability of rejecting the null hypothesis when the alternative hypothesis is true. And the region to the right of this critical value is going to be your statistical power, the 1 minus beta in this case. So just like how I covered the values that you need to consider for significance level, let's also think about what are the critical values you need to know for statistical power as well. The common set of statistical power is 0.80, 0.90, and 0.95. The corresponding critical values is going to be 0.84, 1.28, 1.64. So this is something that you definitely want to know when it comes to thinking about what are the statistical power values you need in order to calculate the sample size. Now let's talk about the calculating delta. So there's often a misconception that the delta in this case is the lift. Oftentimes, when you think about what the minimum detectable effect is, keep in mind that that is represented in terms of lift. So what that means is that it is a percent improvement from the baseline parameter to the new parameter of interest. Let's take a very simple example. So let's just presume that the sign-up rate of the current email form is, let's just say, 50%. And the treatment sign-up rate is going to be 55%. Now, based on the lift, which is the way the MD is expressed, that means that there's a 10% lift from the control to the treatment. Because how do you go from 50% to 5%? Well, that's essentially a 10% gain off of the control sign-up rate in this case. However, in terms of the absolute difference form, that is not going to be 10%. it's going to be 5 percentage point. So that's what the delta expresses, which is the percentage point. So it's important that when you're trying to calculate the sample size, you don't plug in the MDE expressed in the lift form into this delta squared, because they're not the same thing. So this delta squared is the absolute difference between two parameters, as denoted by theta 2 minus theta 1 squared. Now, another thing I just want to quickly mention is that the directionality of how you set the theta parameter does not matter in this case because it's squared. So oftentimes, when we're calculating the sample size, we're also often evaluating in terms of the mean or proportion. In the case of the delta for comparing two means, the expression is going to be mu2 minus mu1 squared. For proportion, it is going to be p2 minus p1 squared. Now let's see how we calculate delta squared in action. Suppose we're given the following problem. Let's suppose that MDE, relative lift, is 20% and the baseline CTR is 15%. What's the delta squared? In order to calculate delta squared, we need to get what is the treatment CTR in this case. And we can derive this from the MDE and the CTR of the baseline. So the MDE is going to be 20%, the CTR is 0.15. In order to get the CTR of 2, or the CTR of the treatment, we apply this following formula. So we can get it by setting the CTR of 2 equals the CTR of 1 times 1 plus MDE divided by 100. The reason why we divide the MDE by 100 is because the MDE is in a percent form. So dividing by 100 gives us the fraction form. And then we add it by 1, and then we multiply this term by the CTR of the baseline, which is 15% in order to get the CTR of 2. So what is CTR of 2? It is going to be 0.15 times the 1 plus 20 divided by 2, which is equal to 0.18. So now that we know what our CTR of 2 and CTR of 1 are, what is going to be the delta squared in this case? So the delta squared is equal to CTR of 2 minus CTR of 1 squared, and when we plug in our values, it is going to be 0.18 minus 0.15 squared, which is equal to 0.0009. So this is an example of how we translate our MDE to the delta squared, which is a required form for the sample size calculation. Now, there's one other parameter we need to cover, which is variance. And variance is not that straightforward because you can't just simply plug in values as a way to get the corresponding values. You have to think about how you're estimating the variance. In order to do so, it makes sense for us to first of all understand the variance in a one sample form. So what is this variance formula for the one sample proportion in this case? It is going to be equal to P times 1 minus P. So P is the success rate. 1 minus P is a failure rate. What about two sample case? So the two sample case is going to be the following. It's going to be the pool variance, which is equal to P2 times 1 minus P2 plus P1 times 1 minus P1. The subscript in this case represents sample size, 1 representing group 1 and 2 representing group 2. And pool variance means that you're summing the variances of the two groups. Now, what about for the mean case? So when you're trying to estimate the population variance, you need the sample variance form, which is S squared, and that is equal to the summation of I equals 1 to K, K representing the sample size in this case, Xi minus X bar representing the sample mean, squared. And this is divided by K minus 1. The reason why you would divide it by K minus 1 is because it gives you the unbiased estimation of the population variance. Now, when you're trying to calculate the sample size that is required for two sample means, the formula is going to be the following. You simply take your baseline variance, which is the S1 squared in this case, and you would multiply it by 2 to get the pooled variance for the two sample case. You might be wondering, why can't you calculate the sample variance of group 2 in this case? The reason why you can't do that is because you don't know what the sample variance is of group 2, which is often the treatment, until you've actually run the experiment. Think about the sequence of designing an experiment. Even before you gather your data for your treatment in this case, you have to preliminarily calculate your sample size. And the sample size calculation requires you to know what your variance is. So in a way, it is a little bit of a chicken and egg problem. On one hand, in order to know what the sample size is required for your A/B test, you need to know what the variance is. Yet unless you've actually run the experiment, you wouldn't know what the variance is for the treatment. So that's why it's important to note that this variance is ultimately an estimation. It is an approximate estimation of what you expect the variance is going to be. And that's why you would multiply the sample variance of the baseline condition, which you can gather through the current performance, and multiply by 2 in order to get what is a pool variance, the pool variance that you would plug in to the sample size calculation formula. Now, there's another final point that I like to make when it comes to the sample size formula. Oftentimes, you might see it in this following form, which is that the sample size per group approximates to 16 times the variance divided by delta squared. Now, one thing I want to let you know is that this is an approximation of the sample size per group in the test for 2 sample means. But where does this 16 come from? So that's something I want to clarify. So what this 16 comes from is the assumption that you're trying to calculate the sample size based on common parameter values of interest. The alpha being 0.05 and the beta being 0.2, meaning your statistical power in this case is going to be 0.80. And the variance form, because it is the 2 sample mean, this is going to be the pool variance, 2 times the sample variance, as I mentioned a minute ago. So when we plug in the following values, what we get are the following. So for the z critical value at alpha equals 0.05, it is going to be 1.96. And the z critical value when the statistical power is 0.80, it's going to be 0.84. And the pool variance in the 2 sample mean case is going to be 2 times the sample variance. And this is divided by the delta squared. So when we simplify this, the value that we're going to get is going to be 15.68 times your sample variance of your baseline condition divided by delta squared, which approximates to 16 times the variance divided by delta squared. So hopefully this provides additional context in terms of a popular formula you often see when it comes to sample size calculation. All right, so now that you have an understanding of how to calculate the sample size, let's apply this in an actual A/B testing example. Suppose that in an A/B test, the desired MDE in a two-tailed test is 10% at the significance level of 0.05 and the statistical power of 0.80. Given that the baseline mean is 10 and the variance is 20, what is the total sample size required for the experiment? Assume that there are 2 groups. So this question is a bit of a mouthful, so we're going to deconstruct this as a way to make sense of this. So what we know about this test is that it is a two-tailed test comparing 2 means in this case. We have some baseline, we have the treatment. And the significance level is 0.05 with the statistical power being 80%. And the MDE is 10%. So what this means is that with the baseline mean at 10, we want to see 10% improvement in the treatment case. And we want to validate that with statistical significance. So the main question is, what is the total sample size required for the experiment? So keep in mind that we're trying to calculate the total sample size, not just the sample size per group. In this case, we have the 2 groups, the control and the treatment. So ultimately, we would try to find out what is the sample size required on a per group basis and then multiply it by 2, because the sample sizes for the control and the treatment are the same. So we start with the following formula, which we have discussed before. The n equals the z critical value of alpha plus the z critical value of statistical power squared, the sample variance divided by delta squared. We're going to divide and conquer. We're going to first of all figure out what the critical values are, the delta, and the variance as a way to get the sample size required on a per group basis. So what are the critical values? The critical values for the alpha in this case is going to be 1.96. The critical value for the statistical power is going to be 0.8. What about for the delta squared in this case? So our baseline mean is at 10, and our MDE is 10%. So what that means is that we want to see the treatment mean at 11. And given that the baseline mean is at 10 and treatment mean is at 11, the delta squared is going to be 11 minus 10 squared, which just gives us 1. What about for the pooled variance? It's going to be the pooled sample variance, which is equal to 2 times the sample variance. And we know that the sample variance for the baseline is 20. So we simply take 2 times 20, which gives us 40. So we know what the critical values are, the delta and the pool variance. We now have all the values we need in order to calculate what is the sample size per group. The sample size per group becomes the following. It equals to 313.6, which we need to round up in order to accommodate for the decimal. So the sample size we need on a per group is 314. Now the question ultimately asks us, what is the total sample size required for the experiment? So we simply take 314 and multiply by 2, which gives us 628. So that is the total sample size required for the experiment. So there you have it. So hopefully this provides comprehensive details in terms of how you calculate the sample size per group in an A/B experiment. If you want to learn more about this, make sure you check out datainterview.com, and there's an A/B testing course which covers more in-depth details along with coding exercise on A/B testing. Please give a like if you found this video helpful, and I'll see you in the next one.